building blocks with AWS, something like that?
Ah, we're actually building a RoboMaker app right now. It's time for our Twitch show to begin.
Oh, okay. Can I watch?
Sure.
Oh.
Do you want to join the fun?
I'd love to, actually.
Okay, cool,
Excellent.
awesome. Let's get started.
All right, let's do
Yeah.
it. We'll get Oz to watch here as well.
Oh, that's a great little robot you have there.
Yeah.
All right, so I guess we're just gonna go ahead and get started. Hey everybody, thank you so much for joining us. We're here to talk about AWS RoboMaker, and we'll go ahead and introduce ourselves. So I'm Alejandra, and I work here in developer relations, and then I'll let Tim and Jeff introduce themselves.
Hi, I'm Tim. I'm a developer on AWS RoboMaker.
I'm Jeff Barr. I'm VP and AWS Chief Evangelist, and I write the AWS blog.
Awesome. Well, all right. Well, let's talk a little bit about what we're building today. So maybe we should start off by explaining a little bit about some of the technologies that we're going to be using. So for RoboMaker, we will be using something called ROS, which stands for Robotic Operating System. And currently we're going to be using Python for our development work. You do have the option to use C++ if you wanted to, but if you're a beginner and you're just starting out, Python should be just fine for what we're doing, huh?
Yeah. So ROS, as you mentioned, is Robotic Operating System, and it's an open source framework for building robot applications. And the way it works is that your robot, it has a whole bunch of nodes, and each little component of your robot, say like the vision of your robot or the wheels of your robot, or every little component is a ROS node, and they all talk to each other with messages. It's called a publisher-subscriber system, if you've heard of that before, and it makes developing robots really easy, and you can produce them in little components, and so you're not overwhelmed with this giant application when you're building a robot.
Oh, cool. So we should probably talk a little bit about what we're building today. We're going to be building a Hello World app, and it does work with all of AWS simulations for RoboMaker, so that's pretty cool.
Mm-hmm.
And it also works with fleet management tools. Today, everything that we're building is actually going to be fully available in a public GitHub repo, so it'll be open source. And we'll show you guys the link later on so you can pull it down and play around with it later if you want.
Yeah, we're really big on open source here.
Yes, that is actually something that the AWS RoboMaker team has been excelling at, and we'll be able to get into that in a little bit.
Yeah.
So, Tim, to get started, usually we need to worry about setting up a development environment. In this case, since we're working with robotics, we'd worry about an Ubuntu development environment. Do we have to do that right now on the show, or is there a simpler way to get started?
Yeah, so the robotic operating system only works on Ubuntu. However, that doesn't mean you need to reformat your laptop and install Ubuntu and set up all the tools and stuff, which can be quite a cumbersome process. Today, we're actually using the RoboMaker Cloud9 IDE, which comes with everything you need pre-installed and ready to go, so you can just log in and start developing your robot without this long, complicated setup process. And you can continue using your MacBook or your Windows machine, basically any machine with a web browser you can build a robot on with.
That's pretty cool. So how much time do you think we're saving by being able to just start right away by spinning up Cloud9 versus having to right now set up a whole new development environment?
Yeah, well, setting up Ubuntu can be quite a challenging process sometimes. It may be a few hours, maybe even a few days to get a full working environment with all the software you need, all the packages and everything just as you like it. And with RoboMaker, you can create a new IDE in just a few minutes. So you can get started quickly and easily.
Oh, sweet. So I guess the first thing we need to get started is to clone our empty sample application.
Yeah.
All right, so
Yeah, let's get started.
as we mentioned earlier, this GitHub will be available for you, so we should probably go ahead and show them over the link.
Yeah. So the sample application is available on GitHub, and it's public now. It's under my username, Tim Robertson, and the name is AWS RoboMaker Tutorial Hello World. So you can get started cloning that. But I'll show you how to create a RoboMaker ID now. So if you have your AWS account, when you log in, it'll look like this. First, just type in RoboMaker to find our service, and then it'll bring up the RoboMaker service. And once you're there, in the top left, you can go to Development Environments, and then Create Environment. And from here, you choose a few settings for your environment. It's all nice and easy. And then once you've done that, you'll be put into an AWS Cloud9 or AWS RoboMaker IDE. And it looks kind of like this. Now to get started, we want to open a new terminal and then go to our GitHub repository and then clone this repository into RoboMaker. So we type git clone, and then the repository there, and then we have all the code. We can see this on the left-hand side here now.
Awesome. So now we're taking a look at the directory structure. So for folks who don't come from a robotic background, maybe you're not really sure what this means or what to expect. So if you're a dev watching today and maybe you're a Python or a Node.js, we're going to go ahead and make some analogies for you so that it all makes sense. How about we go ahead and do an overview of the directory and the file structures and kind of explain to them specifically what the robot workspace and the simulation workspace is for.
Yeah, sure. So we have this robot WS folder, which stands for Robot Workspace and Simulation Workspace. And the Robot Workspace contains all the code that is running on your robot. So anything to do with video, making the wheels move, interacting with voice with your robot, everything you can imagine you can do with your robot, all the code is in there. The simulation workspace is actually only used with the AWS RoboMaker simulator, and this has the code for the entire simulated environment that the robot lives in or is exploring. So in some of our other sample applications, you can see some of the RoboMaker sample applications on the welcome page of the IDE. But in some of these, such as the navigation and person recognition or the voice command sample applications, the robot is actually inside a house or a bookstore. And there's bookshelves and there's lamps and there's all these things that the robot can walk around and interact with. And all the code for them and all the model's information for them is stored in the simulation workspace folder. We're not going to be working with this today. We'll probably do that in a future episode. For now, we're just going to be looking at the robot workspace folder.
Awesome. Okay. So should we go ahead and explain to them about some of the other important files that we have here, such as the package XML file or seemake list text?
Yeah. So inside the Robot Workspace folder, there is a source folder, and this contains all the source code. And then inside that is another folder for all the different packages that will run on your robot. So we only have one package on this robot called Hello World Robot. And inside there, it has two main files. There is one called package.xml, and this describes all the libraries and dependencies that your application needs to run. This is similar to
Node.js.
If you used Node.js before, this is similar to your package.json file, or it's similar to the requirements.txt file for a lot of Python applications. The other file is seemake lists, and this is a make file, and this describes how your application is built. So when you build it, like what files are needed, and everything like that.
Should we take a quick look at them?
Yeah, let's have a look inside. So this is the package XML file, so it describes the name of your robot, version of it, description, and then all the libraries that you need to make this robot work. And then the seemakes list is a little bit more confusing looking, but
it definitely looks kind of weird, huh?
yeah. A lot of these are comments that describe exactly what you need to do in it. And so it describes the packages that you need that you want to build, and then any files or config files or anything like that you need with your robot. This is very similar to, if you've done Node.js work before, this is similar to your Webpack file or your gulp file. It describes how everything is built.
Awesome. Okay, so I think that the next thing we need to work on is actually start creating and doing our code, right?
Yeah, let's get started.
Okay.
So we're going to be building the first step, as mentioned before, ROS systems are comprised of nodes. And so we're going to be creating our first node for our Hello World robot. And this node is actually going to tell the robot to rotate on the spot. This is a simple application, but it demonstrates how you can make the robot move around and do things like that. Okay, so to do that, we first create a nodes folder, and then we can create a separate file for every node that we're creating. And we're going to call this node rotate.py.
So all these nodes we can basically think of as these really loosely coupled modules or entities inside of our software robot here.
Yeah, exactly.
And then ultimately when we take that code and we put it in our physical robot, then they're all kind of dispersed out into the arms and legs and sensors of the robot.
Yeah, exactly.
Is that a good way to think about it?
Exactly. And that way your code is modularized, so that you don't, so you can work on each individual component of your robot separately, or you can have a team working on different components and they can all talk to each other. They'll all be separate nodes in a ROS system.
So for each task that you would want your robot to accomplish, you need a new node, right?
For each, often you'll need a new node, and they talk to each other with messages, and we'll go into that in a moment.
Awesome.
Yeah, so to start off with, you need to tell ROS that this is a Python file, so that it can compile it correctly. And to do that, we add a header with hashbang, and then we type /user/bin/env Python. This is just a common thing that goes at the top of every Python file. And then we want to import the ROS Python library. So import ROS.py.
And why are we using this library today? What's so cool about this one?
So this is the ROS.py library is basically all the ROS functionality in Python. So almost everything you need to do, it's creating a node or creating a publisher or sending messages or setting the rate that messages are published, all of that is, all of the functionality of that comes from the ROS.py library.
Gotcha.
So that's generally included in every ROS node at the start. And then we are going to, we're going to create the entry point to this file. So when ROS loads this file, it needs this is a common thing in Python, is it finds this entry point and it does this by this if statement saying if the name that it's trying to call is __main, then we want to call the main function. We haven't created this main function yet, so let's do that now. So to create a function in Python, we type def, and we'll call this function main.
And is that standing for definition?
Yeah, exactly.
Awesome.
Okay, and then we need to initialize this node. So this is called a rotate node, and to initialize the node and to say that that's what it is, we call ROS.py. As mentioned before, like almost every function is on this ROS.py object. And so we call ROS.py init node, and then we want to call this node the same as the file name, so rotate. Okay, and now we want to put all the code for this node to actually make the robot rotate. And we probably want to do that using a Python class so that the code is well structured and people can easily work on it in the future.
So you're being nice to future devs?
Exactly.
I guess that's a good rule of thumb to go by.
Yeah.
That future dev may be your own.
That's true.
Yep.
Maybe that future dev may look at it later and say, what was I thinking?
Yep.
What was I thinking?
Yep. So we'll create a class to make the robot rotate, and we'll call this class just rotator. Okay. And then we need to create a constructor for this class. And that's the first function that will be called when we create this class. And inside this constructor, so the constructor is always called init in Python, and the first argument is always self. For any function that is part of a class, the first argument should always be self.
I love how you're helping us learn not just about RoboMaker, but also about Python.
Yeah.
That's so cool. You guys are getting 2 for the price of 1 today.
And we can also see how easy it is to use Cloud9 to write Python. How helpful it is with all the pop-ups and completions.
It
Oh,
really
yeah.
is, yeah.
Yeah, exactly. So you'll see as we're coding, Cloud9 actually comes up with errors when you've done something wrong, and comes up with little warnings if you say created a variable and you haven't used it yet, things like that, just to make sure that you're on the right track in case you've forgotten about anything when you're developing. So it's pretty good Python support. Okay, so now what we're going to do, in this constructor, we're going to create what's known as a ROS publisher. And a publisher sends messages out to other nodes. And so we'll create that now. So we'll create a publisher called CMD vel publisher. And the reason that we're calling it this is it stands for command velocity publisher. And the TotalBot robots and a lot of the default ROS robots, they actually have a ROS node already running on the wheels of the robot. And the wheels are basically listening to this topic called CMD vel. They listen for any messages telling them to move. And then when they do, they start up the motors and they start the robot moving. So we're creating a publisher to send messages to the wheels of the robot. And so to do that, we type rospy.publisher. That's the kind of thing this is. And the first argument to this is the topic that we're publishing to. So as we mentioned before, the topic is cmd_vel. And this is what the wheels are listening to and what they respond to. And then we need to, the second argument is the type of the message. In this case, it's actually called a twist message.
I really like that name. It's fun.
Sounds stylish.
So we probably need to import that one in too, huh?
Yeah, so the twist message isn't actually declared yet. As we can see in Cloud9, it gives us helpful hint saying undefined variable twist. So we need to import this from somewhere, and we're actually going to import this from the package geometry messages, or message import twist.
Another cool name.
And now twist is available. And so a twist message is, it's basically two vectors. And the first vector describes where if the robot, like the speed, it's called linear, and it's the speed of the robot like forwards or backwards. And the second vector is called angular, and it's the speed of the robot, how much it's turning left or right. And with those two vectors, we can make the robot go in any direction we wish.
Okay. Just to be really clear so I understand this, we are making a publisher that when we use it later, will tell the robot to twist. We're not actually, with this statement, causing the twist. We're just saying we would like to be able to twist at some point in the future.
Exactly, yeah. So we're just initializing the publisher now, and then we're going to use that in a bit to send messages to the robot. Yeah.
So we probably want to worry about queue size now, huh?
Yeah, so the third argument to the publisher is queue size. And this basically says how many messages you can queue up. Say the wheels stop responding because they got stuck or they crashed or something on the robot. We don't want to we generally don't want to lose all the messages that we're publishing to the wheels while they're not working. We want to queue up our messages so that when they come back online, when the robot's going again, then all the messages can be sent to the wheels. In our case, we're actually sending the same message over and over, so we don't need a big queue size, so we can just set that to 1. But in general, a number of like say 10 is generally pretty good. If you make it too big,
you think?
yeah, something about 10. It depends on what robot you're creating. If you make the queue size too big, it uses up more memory. It's not generally a problem unless you're making it in the thousands. But yeah, you want to queue up a few messages just so that no messages are lost.
Makes sense.
So
So now we need to do our main rotate function, don't we?
Yeah. So now we actually need to tell the robot that we need to use this publisher to publish messages to the robot to tell it to rotate. So to do that, we're going to create a function called rotate forever. At least until you shut the robot down.
Or till the end of the stream.
Yeah. So we create a function called rotate forever, and as mentioned before, the first argument is always self. And now we need to create the message that we're going to send to the robot. So we'll call this rotate message, and we'll make this a twist message because that's the type of message that we want to send to the robot. Okay, and now we want to tell the robot that we want it to rotate. And so to do that, as mentioned before, the twist message has both a linear, a thing called linear vector, and then an angular vector. So you can type linear or angular. So we're going to be using angular today, and we're going to set the z value of the angular vector to 0.5. And this is a decent speed for the robot to rotate at. We could set it slower and the robot will rotate slower. We can set this really high and the robot will spin out of control. But 0.5 is a pretty good number for now.
But this is a speed, it's not a target position.
Right. Exactly, yeah. Yeah, this is just a speed that the wheels will rotate at.
Originally, when we were thinking through the show, we had chosen a speed of like 0.1 just to be safe. And it was so slow, you couldn't even tell it was moving. So we're like, well, maybe bump it up to 0.5.
Yeah. Okay, so now we want to keep sending this message to the robot, to keep telling it to keep moving. And to do that, we're going to create a while loop that continually sends a message. But before that, we don't want to have an infinite while loop that just keeps sending messages over and over, because that may make the robot crash. It may just get overloaded with too much stuff. So to slow it down so that we're sending messages at a decent rate but not too fast, we can use this tool called a ROSPy rate. So to do that, we type rospy.rate, and then we set how many messages per second we want to send to the robot. So we want to send maybe 10 messages a second is a good rate.
So this robot is in a single second getting 10 messages at a time.
Yeah.
Do you think it'll feel like we're nagging it?
Luckily, the robot operates on a nanosecond level,
Okay.
so it should be okay with dealing with 10. It'll be okay with that.
It won't break him.
No.
Okay. All right, that's good.
And
so we gotta go ahead with our while loop, huh?
Yeah. So now we'll create our while loop to send the messages to the robot. So to do that, we'll type while, and while not, rospy.is shutdown. So while we haven't shut down this node, while it's still running, we just keep going through this loop. And what we're going to do is we're going to call this this command velocity publisher that we created before. Luckily, Cloud9 auto-completes a lot of these variables for us, making coding easy. And we want to call the function publish on this publisher. And we want to publish the rotate message. There we go. And so we're sending that to the robot.
What about logging?
Yeah, that's a good point. So we probably want to also have some logs so that we can debug whether it's actually sending the message or not. And so to do that, we can use rospy.loginfo. And this will log out an info message. And it's very similar to the Python print command. And so we'll just say we're rotating the robot. And then we'll publish a string. And the string will be the rotate message so that we can see what we're actually sending to the robot.
So can we think of all these different node functions as running as separate parallel Python threads?
These all run in one thread, but yeah, if we have multiple nodes, so if we had, say, a camera node or something, yeah, they can run in different threads on the robot, and then yeah.
So we can have while loops, and we're not going to leave the rest of the robot starved for cycles.
Yeah, so this node will run in a separate process, and then only it will be stuck in the while loop.
Cool.
Yeah. And now we need to use this rospy rate. You can see Cloud9 has helpfully informed us that we haven't used this variable r yet. So to do that, we can do r.sleep, and that will make the robot sleep for that amount of rate. So it'll sleep for basically 0.1 of a second.
So this is a good safeguard against the crashing scenario that you were mentioning earlier as well.
Exactly, yeah. Yeah, we don't want to continually send messages to the robot, so a 0.1 second break is good enough for the robot.
Awesome.
So we've created this rotate forever function now, but we haven't actually initialized this class or called the function yet. So we can do that in our main function here. So to do that, we'll type rotator. We'll create a new instance of this class, rotator, and that is a new rotator. And then with this rotator, we'll call rotate forever. And then we're done. We've created our rotate node. It's created an instance of the rotator class, and it's called rotate forever to continually send this message to make the robot rotate.
So we wrote our very own rotate.py file, and do we need to worry about updating a few other things now, like I think the launch file, probably?
Yep. Yeah, so we need to, we've created this node now, and we need to actually make ROS launch it when it runs this package. To do that, we create a thing called a launch file. And like the nodes directory, we create a new directory called launch. And inside that, we will call this launch file the same thing as rotate, but it has the extension .launch. So rotate.launch.
I know, I was really surprised when I first saw that extension. I'd never seen that before.
Yeah. Yeah, this is ROS specific, and it describes how to launch all the nodes in your system. So if we had like 10 different nodes, this launch file can describe like the order that we launch the nodes in, any configuration settings those nodes need, things like that. It's the main thing that ROS runs when it runs your application.
Okay. So this then executes the main function of each of our node functions, and then how do we get the intent that we want to actually get that rotate function activated?
Yeah.
Or am I getting ahead of things here?
Yeah, we'll start coding that now. So the launch file is an XML file, and it describes all the nodes, and then what will actually be running on those nodes. So the very first thing we need, because this is an XML file, we need a launch tag. And Cloud9 helpfully makes the ending launch tag after that.
Cloud9 has been very helpful today.
Yeah.
That's awesome.
And then inside this launch file, we want to say that we're launching a node, and this node comes from the node takes a few parameters, and the first one is the package that the node is inside. So if we can actually download other packages from the internet. Say we might have a LiDAR package, and we can put that in here, or we can include it in our application, and then we can actually launch nodes from that package as well in our launch file. So we can launch nodes from all these different packages, and they'll all run together on our robot. And so this package is, as mentioned before, it's called Hello World Robot, as it's that's the folder name inside this source folder. So and it's also written in the package.xml file, this name here. So say it's Hello World Robot, and then we need to set the type of the node, and the type of the node is basically just the file name of the node. So,
which, as you may remember, it's the rotate pi that we just created.
Yep. Yeah. So do rotate.py, and then we want to call this node rotate.
And what about the output?
Oh yeah, so we want to be able to see these log files, this log info that we put in here. By default, that just goes to a log file on your computer. But if we run this in the terminal, we probably want to see the logs and see what's happening. And so to do that, we can say the screen, the output of this node goes to the screen, so that all the logs will appear on the screen.
Awesome.
And then we're done on our launch file.
So I think now we need to update some of the dependencies in our package.xml file, right?
Exactly, yeah.
Okay.
So,
as you may remember from the rotate pi file, we had imported some stuff from the geometry messages, I think it was.
Yep.
So we need to go ahead and add the dependency to our file now.
Yep, exactly. So we've created our launch file and our rotate. So yeah, we'll open up the package file, and as you mentioned, we're using this package geometry messages, but it's not currently specified in this package XML file. So to import that, we can add a new thing here, depend, and we're saying that we depend on this package geometry messages. So I'll just go there, copy that, and paste it in here. And then when we download all the dependencies for our application, it'll make sure to download geometry messages so that we can send the twist message to our robot.
Okay, awesome. So we wrote our rotate pi file, we've updated our dependencies, and I think we need to also update the seemake list text file, huh?
Yeah, exactly.
Yeah.
So we need to update this file to say that when we're building our robot, we need to include those geometry messages, and that we also need to include this new node that we just created. So to do that, we go into two spots in here. So there's a find package, and in here we need to say that we want to find the package geometry messages when we're building. And then there's also another section, catkin package, where we say that we need geometry messages.
And what is catkin?
Yo, I was just about to ask that.
So catkin is the ROS build tool for ROS 1 applications. It's pretty commonly used. We actually use a tool called Colcon though. And Colcon does the same thing as catkin, but it works for both ROS 1 and ROS 2. We'll be describing ROS 2 in a future episode, but it's the next generation of ROS that's still in early stages, but it'll be out soon. And so we wanted to use this Colcon tool so that we use the same tool for building all of our packages, no matter what version of ROS we're using. Okay, so we want to include geometry messages there. And lastly, we need to include our node in here. So we need to say nodes/rotate.py, and that'll make sure that when we build this application that the node is included correctly.
Okay, so I think we wrote all the code we needed to for this specific demo, right?
Yeah.
We did it. Thank you, Tim. Okay, well, we're not done yet. We still need to worry about building and bundling now, right? Seems like the next few steps in line.
Yep.
So for folks who are watching the show later on, you wanted to download the GitHub repo and take a look at this and try it on your own. The README in the GitHub repo does have the instructions of everything that we're about to do right now. So we should probably go ahead and do that next, huh?
Yeah.
Okay.
Yeah. So
there's still one missing part I'm not getting.
Okay.
How do we know what actually calls the rotate method?
Oh, yeah. So when in this rotate.py file, when ROS calls this, it sends in this message saying we're looking for the name main, and so it goes into this if statement straight away, and then it calls the main function here. And then that calls the
okay. So as soon as
node.
our robot comes to life, it's just going to start spinning around.
Yeah,
Okay.
exactly.
Right.
Yeah.
Got it. Okay.
And so we can actually we can build this now. So if you have a look in the GitHub repository, the tutorial Hello World, you'll notice in here One thing I didn't mention at the start is I've actually created separate branches for here for each step that we just did. So step 1 is creating the node, step 2 is creating the launch file, step 3 was updating the package XML, and step 4 was doing the seemake lists file. And so if you get stuck at any point, you can jump to that step and see what code we wrote and have a play around with that. But once you're done, once we've created all this, our application is actually going to look very similar to our AWS RoboMaker sample application, Hello World. And so this is linked in the README file. So you can open this up. And this application has all the commands for building and running your robot. So we need to run a few commands, and what these are doing here is they're getting the packages that we need off of the apt repository. So that's the same repository that you download your Ubuntu packages from if you've used Ubuntu before. And then these commands also install any dependencies we need. And then, as mentioned before, we use this build tool called Colcon, and that will build the application. We've already, ahead of time, downloaded all these dependencies, so we can go ahead and build the application now. So we'll go back to the Cloud9 IDE, and then we'll cd into that folder, and then we'll cd into the robot workspace folder, which is where we're building, and then we can run colcon build, and that will build all of our code. And this gives a little warning about catkin, but that's okay because we're not using catkin there, so that one can be safely ignored. And so the build is done. It only took 3 seconds.
3 seconds to do a whole build?
Yeah.
Cool.
It does take a little longer if you have a lot of packages or a lot of dependencies for your application. But because this is a simple application that only has one node and no dependencies, except for the geometry messages, it can build in just a few seconds.
Okay, cool.
So now what we can do next is we can actually run this in Cloud9. We won't actually see a robot spinning, but we can just make sure that this log message is coming out so we can see that it's doing what we expect of it.
So basically, at the end, we won't have a physical robot like Tim was saying rotating here in this specific episode. But once we launch the simulation, that was when we'll get to see our rotate file actually work.
Yep, exactly.
It wasn't, all this work wasn't in vain. We will see some robot.
To run it in Cloud9, we first run this source install / local setup.sh. And this is a common thing that you'll do in ROS a lot. This local setup sh file was created when we built it, and it sets up all your environment variables and everything that you need to be able to run the application correctly. So we first run that, and then to launch our application, we use the command ROS launch. This comes built into the Cloud9 IDE, or when you install ROS, if you install ROS on another Ubuntu system, this will be on your command line, so you can just use it straight away. So we'll call ROS launch, and then we type the name of the package. So it's Hello World Robot. And then we type the file that we want to launch. So we want to launch the file rotate.launch. So we run that. And here we go, it started, and it started rotating. And we can see that it's sending a lot of messages. It's sending approximately one every 10th of a second, or 10 per second. And these messages have...
The robot's just like spinning around.
Yeah.
That's exactly what it's doing.
Yeah, and so it's sending, we can see it's sending a linear vector of all zeros and an angular vector of, with the z is 0.5. And that's saying that the robot will spin, to the left.
Awesome. Okay, so what's next, Tim?
Yeah, so up next, so if we want to run this in RoboMaker, we need to run another command, and that's called colcon bundle. And what that does is it takes all the packages, all the files, everything you need, and puts it into one tar file. And then you can send that tar file to other places, and like say the RoboMaker simulator, and it'll have everything it needs to run your robot and simulation, everything like that. This does take a little bit of time. It takes a few minutes to run colcon bundle. We've already got this environment here that has it all pre-run.
You got a few things ready ahead of time this
yeah.
have that cake already cooked in the oven.
Exactly. So we've bundled it in here. And then to actually run it in RoboMaker, you'll need to create an S3 bucket and put your bundle up there. And unfortunately, the RoboMaker can't pull the files from your IDE. So we need to put it in a place that it can access all the files. So to do that, we can use the command line. So we can go into our tutorial folder and then into Robot Workspace. And then when you run Qualcomm bundle, it creates this file inside, it creates a new bundle folder that we can see here. And then inside this folder, it creates a file called output.tar. And this is everything that your robot needs to run.
So that's the one we need to move over to S3.
Exactly.
Awesome.
Yeah. So to do that, we type AWS S3 copy. And we want to copy this file bundle/output.tar. And we need, so you'll need to create a bucket beforehand. You can do that through the AWS console. So in here, you can go services and then S3 and then create a bucket that way. And if you do create a bucket, Cloud9 will automatically be set up with all the credentials that you need to copy files to that bucket and work with it. So we want to copy this file up to the bucket. We've called this bucket the same name as our GitHub repository. You won't be able to access that bucket yourself.
Right. Unfortunately.
Yeah. But this will be your own bucket.
Well, let us know right away if you can.
Yeah. And we probably want to call the file robot workspace to be the same as up
Directory
here.
structure.
Yeah, and then we call it robot.ws.tar. We've actually already uploaded this bundle to the bucket, but I guess we can just put it up there, and then it'll copy the files up, and it'll be ready to go. Once we've copied these files, so you'll need to build the robot and the simulation. The simulation should be all ready to go, so you can just go into the Hello World README, and it gives the instructions on how to build and bundle your simulation as well.
That file that we just generated and uploaded, is that effectively a memory image that we would just upload if we've got a real robot? That's the memory image that has the operating system and our code and everything just ready to go for.
Yeah, it doesn't have the operating system. It's only the robot code and packages. So when you're running it on your robot, you'll need to install either Ubuntu or some flavor of like Raspbian or something on your robot, something that has ROS on it.
So as long as it's ROS compatible, it should be good to go, right?
Yeah, exactly.
If you're wanting to use AWS RoboMaker, of course.
Yep.
Which of course you do want to use.
So yeah, so if as long as you have ROS on the robot, that'll be able to read this file and understand what to do with it. Although there is a difference. If you want to run this on a Raspberry Pi robot, you do actually need to build it using a different build format. It's called because the Raspberry Pi chips are ARM chips, you need to build it in a different way. And this is described in the README file of Hello World. Yeah.
Awesome. So for the simulation environment that we're going to open today, we're going to be using something pretty basic. It's called an empty world simulation, right?
Yep.
So we're going to have an empty world in which to rotate our imaginary robot. So it's going to be a lot of fun. Basically, it just looks kind of like a grayed out Matrix, I feel like that's what it looks like. Anyway, we'll see it soon enough. So what do we need to do next in order to be able to spin up our simulation and actually see our robot spinning?
Yeah. So to do that, we need to go to back to RoboMaker in the console. And then on the left, you'll see there's robot applications and simulation applications. So we can create our robot application first by going there and then clicking Create Robot Application. And in here, we can call this any name you like. So just Twitch Demo Robot. And then we choose the type of software that's running on the robot. Currently, ROS and Kinetic is the best option. They're the only options at the moment. But in the future, if you're seeing this in the future and there's more options, ROS and Kinetic is what you should choose.
If you're watching our stream in the future.
And now we need to point to the file where we uploaded that bundle. So
sorry, S3 bucket, right? That we created a second ago?
Yeah, exactly. The output file. So we can go back to here and we can just copy this, the place that we uploaded the file to, and then we'll go back to RoboMaker and we'll paste it in there. And it'll just check that the file is valid and warn you if it's not. And then we click create.
Ooh.
And then this creates our little robot.
Awesome.
And
Success.
then yeah. And then we need to go to we need to create our simulation application.
So for our simulation environments, we're using Gazebo, right?
Exactly.
And Gazebo is actually maintained by the same foundation that is maintaining ROS.
Yep.
So the RoboMaker team is actually doing a lot of great work with that foundation. So today you get to see a little bit about what that looks like.
Yeah. And so to create our simulation application, you'll need to go through the instructions in the Hello World README to build and bundle that. And then we can call this, say, Twitch demo simulation. You can call this anything you like, and choose these settings. So Gazebo version 7, rendering engine of Ogre, and rendering engine of 1. And then we need to point to where this file lives. So this is very similar. We've already uploaded this file. This is very similar to it before, but we called it simulation workspace.
And there was a whole separate source code tree that defined that simulation we didn't really explore.
Yeah, exactly. So that was in this simulation workspace folder. That looks very similar to the Hello World folder. It's just a Hello World simulation. And it has its own launch file, and it launches just a world called Empty World. So we can create the simulation here. And then once we're done creating the robot application and the simulation application, we can create a simulation job. And a simulation job just basically takes both of those and puts them in a simulated world. And so we can see the robot moving around and spinning on the spot.
So we actually got this ready ahead of time too, didn't we? Like a good 8 hours before minimum.
So this takes maybe 2 to 5 minutes to start up generally. So we didn't want to be waiting around. So we've actually already run a simulation. And we can jump over to that now. So we'll go, actually it's already on this page, so we can see that it's running. So we can jump into the simulation. And when your simulation is running, you'll see that you have all these tools that you can use to interact with the simulation. So there's Gazebo, which will allow you to view the robot in the simulated world. And then there's RQT, RViz, and a terminal, which just give you additional tools to interact with your simulation and work with it. We'll probably go into them in a future episode. But for now, let's see what we've created.
I'm done.
Here we go.
Is it rotating?
Awesome.
It is.
Oh my goodness! Yay! All right, so we successfully got a robot to rotate, and as you can see, it really does look like the Matrix, doesn't it?
It does.
So Tim did mention earlier that there's some really cool libraries that the world can look like a house or a bookstore and whatnot. That said, even though we didn't use one of those today, there are still some fun little things you can add on to here. I honestly think this is probably one of our favorite parts at the end.
Yeah.
So you see over here, you can actually do things like actually change the view angle in which your robot is in its world. So if I were to do that and maybe go, hey, you know what, let's switch over to here, boom. Mm-hmm. And so it's actually kind of cool to be able to visualize the world from the robot's perspective, right? Because the robot's perspective is very different from the way you and I view the world. So I'm gonna go over back to this view, and actually this one is better. I think I like this one more. So then the other cool things that you can use, you can actually add lighting elements to your world. So if I were to click on lighting elements and then start adding a few things like fun shapes. Did I just squash my... Oh my goodness! Well, and it died.
We've got Still there.
Okay, there it is. I think we should probably move that.
So we can, this will allow you to place like a sphere in the world. So we can put a sphere there, and then we can see
And then we can see a little light element there.
Yeah.
Really cool.
Yeah. Now we could have also put these in our simulation inside of Cloud9, right?
Yeah, exactly. So we can, you can add them in that simulation workspace. You can add them in there, and see things.
There's another one.
Ooh. There we go.
So months before reInvent, when I was writing about RoboMaker, I got all set up, and I actually bought a Turtlebot 3 and put it all together, and I never actually got the next step of actually putting code on it. So what do I need to do next? We've got the rotate, I've got the Turtlebot 3.
Yep.
What are the steps in between
The next step
empty
is
Turtlebot and spinning Turtlebot?
The next step is to tune into episode 2.
So we don't have a Turtlebot with us today, but I can show you how to set it up on a robot. So yeah, RoboMaker, that's a good point. RoboMaker actually has a lot of really good tools for deploying straight to your robot. And this uses AWS Greengrass and AWS IoT to get the files onto your robot. And you can do this through the RoboMaker fleet management tools. So we'll just go back here. And on the left, you can see there's a fleet management tab. And here, you can set up robots, you can set up fleets, and you can deploy to your robot. And so we have a little Assyrian test robot that we were testing on earlier. The idea is that you can actually have a fleet of, say, 100 different robots in a warehouse all running the same software. And you can deploy your code, you can make a code change, and you can deploy it to all of the robots automatically. You don't have to manually copy files to every single robot. It'll just handle it all for you. And you can even do things like rolling out the code to like just some percentage of your fleet at a time. So if you want to test a new change on like 20% of your robots, you can do that through here. So to do this, you can go to Fleet Management and Robots, and then create a robot. You can give it a name, my robot. And then you have to set up Greengrass on your robot first. In Greengrass, AWS Greengrass is a tool that connects your robot to the AWS cloud. And we use that for the deployment and everything. And so we create the robot, we choose what type of robot it is. So if you're running on a Raspberry Pi, it'll be HF, but otherwise x86 for other computers. We can you choose the Greengrass group that you're sending it to, and then create your robot on here. Okay, the Greengrass group is already in use, so I guess we need to create a new Greengrass group. So we'll call my robots, and we'll choose a role, and we can create that group, that robot. And then it'll give you, once you've created your robot, it'll give you these the software that you need to put on your robot to automatically connect back to RoboMaker. So we'll just skip that for now, but you just download that and then go onto your robot and put it on there. And then you can add your robot to a fleet. So you can create a fleet of robots. So you can add new robots to your fleet, and then you can create new deployments to your fleet. And so if you want to deploy that application that we just made to your fleet, all you have to do is go create deployment, choose that application that we just made, the Twitch demo robot or tutorial hello world robot. And then you choose the launch file that's launched when you are, so that's the launch file is the rotate.launch, and the package name, which is hello world robot that we did before. And then you can deploy it to your robots, and you can choose like how much % of the robot fleet you want to deploy to, and so on.
That's crazy. You can actually choose a percentage of your fleet.
Yeah.
Really cool.
Yeah. So we want to support people in any use case. So even if you have large fleets of robots, you can use RoboMaker to manage them.
So in theory, I could take my Turtlebot 3 and I could run recognition on it, and I could look for my dog, and I could chase my dog around the house?
Yeah.
You can. We're actually thinking about doing an episode on that later on. I don't know that we actually got to the part about chasing the dog to the house, but maybe we can add that in.
Yeah.
Okay, so first of all, thank you so much, Tim, for answering so many of our questions and just really walking us through it. It was a lot of fun listening. We really got to learn a lot of really cool things. So let's just do a really quick recap of what we did today. First of all, we got to learn a little bit about the robotic development environment. We learned about what ROS is. We also learned about different ROS packaging options. We heard a little bit about the different contributions that the AWS RoboMaker devs have been able to do. We also learned how to spin up our AWS RoboMaker IDE, because now we know that IDE is great and it'll save us a lot of time and it'll be really easy to develop with it. We also learned how to spin up the Gazebo simulator and just kind of check out an empty world simulation there. And we learned how to build and deploy our very own Hello World AWS RoboMaker app. So I think we did a lot of really good work today. That said, there's apparently one last thing on the to-do list that we still need to take care of, don't we, Tim?
Oh, yeah.
Yeah. So, Jeff doesn't know this.
This sounds ominous.
We actually have a surprise for Jeff.
Oh, cool.
We have a surprise giveaway for him. What do you think it is?
A robot?
Oh, not quite. But...
Oh, awesome. Awesome. A dinosaur. Very cool. Thank you so much. This has been a blast.
And from the kit, you can actually make 3 different dinosaurs.
I absolutely will.
Well, thank you so much for being here, Jeff. It was a lot more fun with you.
Totally fun.
All right. Well, thank you guys so much. And again, the next episode will be on May 15. And in that one, we're actually going to learn how to hack into your robot and how to implement better security features into it so you don't get hacked. All right.
Cool. Thanks.
Thank you.
Thanks. Cool.